Hello everyone, my name is Dr. Julio Peña-Aguirre from the Universidad Politécnica de Guanajuato, and I am honored to present our collaborative work entitled Physiologic Power Management Strategy for an Electric Vehicle. This research was carried out jointly with the Dr. Francisco J. Pérez Pinal from the Instituto Tecnológico de Celaya, Master Tomás Serrano-Ramírez, and Dr. Roberto Zarate Espinosa, both from the Universidad Politécnica de Guanajuato. The presentation is structured as follows: introduction, justification, objective, system description, physiologic control, voltage and current control, results, discussion, conclusion, reference, and finally, acknowledgement. Introduction. Transportation remains one of the largest contributions to greenhouse gas emissions worldwide. Electric vehicles provide an alternative, however, their performance depends heavily on the energy management among the fuel cell battery and supercapacitor. To ensure stability and longevity, an energy management system is essential to balance power and maintain voltage regulation under dynamic driving conditions. Justification. For this work is based on the growing need for intelligent energy management strategies in electric vehicles. These strategies make it possible to optimize the power distribution among the different energy sources, in this case between the fuel cells and the supercapacitor, which directly improve the vehicle performance, autonomy, and component lifespan. However, traditional control methods often struggle when facing nonlinear or fast dynamic change. That is why the fuzzy logic is proposed as a viable and raw solution. It has the unique ability to handle uncertainty and adapt to continuously changing driving conditions without requiring a exact mathematical model of the system. The objective is to design and validate the physiology-based energy management system for a full cell electric vehicle by the supercapacitor. Validation was performed through the hardware in the loop hill experiment of a Typhoon Hill 402 platform, ensuring real-time response and interaction. Electric vehicle structure. The figure 1 shows the electric vehicle structure. The fuel cell converts hydrogen and oxygen into electrical energy through a chemical process. That energy passes through a DC-DC converter. We can show it in the figure 1. That regulates voltage for the DC-DC bus. This is the converter which regulates DC-DC bus. A supercapacitor connects in parallel to supply energy during acceleration and absorb power during regenerative braking. Currents are labeled as I-conv. Convert the current from the fuel cell. Drive currents delivered for the inverter and traction motor. And ILC, current flowing into from the supercapacitor. This is which is this. On the right, DC-AC inverter, drives the AC machine. That is why. This setup allows the power sharing between the sources, improving efficiency and transient response. Fuzzy logic-based control. Figure 2 displays the fuzzy logic control structure. It uses three main equations. Supercapacitor current, ISC, is equal I-conv minus I-drive, indicates charging or discharge mode. Supercapacitor power, PLC, this is equation 2, is equal ILC is the current supercapacitor multiplied by B bus, that represents the power exchanged by the supercapacitor. And finally, the equation number 3 represents the converter current, which is I-conv is equal P-conv, the power from the converter, divided by B bus, which defines the current supplied by the converter based on its power and its bus voltage. This relation serves as input for the fuzzy logic block, which outputs P-conv optimize the converter. Fuzzy logic-based control. This slide represents the fuzzy logic-based control system, which defines how the converter power is regulated using a nonlinear decision surface. The fuzzy interference system uses two input variables, the supercapacitor power, PLC, and the state of charge, SOC, and produces one output variable, the converter power, PCOM. Each input is divided into four linguistic sets. low, medium, low, medium, high, and high, generating a total of 16 rules that describe all possible operating scenarios. These rules were designed following the Mandani type interference method, where each rule is activated by the degree membership of the inputs. The rules are combined through the fuzzy aggregation, and the final output is optimized by the centroid fusification, producing a small control signal. On the right, the 3D surface plate, figure 3, illustrates the behavior of the fuzzy controller. It shows how the output power becomes changed smoothly as the function in the input SOC and PSC. The surface demonstrates that when the SOC is low and PSC is negative, the converter provides more power to recharge the supercapacitor. When SOC is high and PSC is positive, the converter output is reduced, allowing the supercapacitor to assist during acceleration. These small transitions across the 16 rules ensure continuous and adaptive control without abrupt change, improving energy efficiency and reducing stress on the power components. The voltage control. Figure 4 displays the voltage control diagram and the question 4 to 8. The control regulates VBOS according to the motor speed using a proportional gain Kp 0.03 and tau equals 7 for a stable response. The most important equation that we can display in this case is the equation number 4, equation number 6. Why? That's the reason. The equation number 4 is the equation that demonstrates or is how can we obtain the boost voltage reference that is equal a boost voltage match minus the gain 1 multiplied by the angular speed from the engines. And the number 6 is the equation that it represents the energy from the supercapacitor. K1 is the gain, and this is obtained by the relation, the difference between the volts maximum and minimum between the angular speed maximum. Another important equation is the 7, that this is the transference function from the system, or in this case from this for this control. Current control. The figure 5 illustrates the current control diagram, which regulates the electric current supplied by the converter to maintain voltage stability on DC bus. The control starts from the mechanical power (PMEC) required by the motor. This signal is integrated twice to obtain angular velocity and torque components, then divide to generate the reference proportional to the motor power demand. The main purpose to average motor current demand, creating a smooth converter reference and minimizing bus voltage oscillations. This method eliminates the need for the torque sensor, simplifying implementation and reducing hardware cost. Results. Figure 6. Figure 6 shows the dynamic performance and speed profile of the simulated vehicle. The curve corresponds, the figure 6 corresponds to the ICI 15 driving cycle, representing the urban driving with frequent acceleration, cruise, and braking phases. The maximum vehicle speed reaches 120 km per hour, effectively testing transient conditions. The table below summarizes the simulation setup. Samples of a total of samples 1,180 samples. Sample simulate 1 second. Machine and electrical parameters. Rated torque 15 newtons meter. Torque 100 newton meter. Base speed 2,850 rpm. Maximum speed 9,000 rpm. Voltage range is 1040 to 2010 voltage. Supercapacitor capacitance 32 farads. These values represent the actual physical limits of the driving train components, ensuring the simulation accuracy before real-time hill testing. Results. The figures 7 to 9 compare the current performance for the strategies. In the current control, which is the figure 7, peaks near plus 50 amperes, supercapacitor discharge minus 35 amperes, unstable high stress. The voltage control strategy shows moderate oscillation, approximately 20 amperes, slower transient recovery, and the fuzzy control converter is approximately 10 amperes, supercapacitor 10 amperes, positive minus, so, smooth and stable response. The maximum converter current is reduced from the 47 amperes current to 7.5 amperes, proving that the fuzzy logic controller effectively limits peaks and exchange relativity. Results. The figures 10 to 12 compare the voltage stability. Again, the current control strategies large drop from the 2010 voltage to 1040 voltage unstable. The voltage control average 2000 minus plus 20 voltage, fuzzy control stable around the 2005 voltage with less than minus plus 2 voltage in the case of the fuzzy strategy. This demonstrates that the fuzzy controller is superior voltage stability and power balance. The second comparison shows that the fuzzy control keeps the supercapacitor with 94 and 97%, ensuring optimal energy reserve and preventing over discharge. Current control fluctuates excessively with the voltage control is too conservative. As in summary of the three strategies, fuzzy control fast but unstable, fuzzy logic control stable, adaptive, and efficient. Is that the 205 voltage boost presents approximately 7.47 amperes peaks. The fuzzy method achieves the best overall balance, and the voltage control is smooth but slow. In this section of the discussion, analyze two dynamic performance indicators, MPD and APD. That is, we can see in the table 1. This MPD is represent the maximum power derivative that represent the maximum rate of the change of the power during a low transience. High MPD means that the fast response but too high can cause stress. The APD is the average power derivative over time, indicating smoothness and energy efficiency. Lower APD implies small power exchange and reduced losses. Fuzzy control results MPD is equal to 54.7 amperes per second, quick response to load variation, and APD 12.3 amperes per second, small stable energy flow. Compared to current and voltage control, the fuzzy approach provides the best balance between the fast reactions and low oscillations. Conclusions. To conclude with the key insights of this research, first, the fuzzy logic enables efficiency and flexible energy management in the fuel cell vehicles. Its rule-based design adapts dynamically to changing load conditions, ensuring both stability and responsiveness. Second, in achieve an excellent balance between the dynamic response and computational simplify, maintain 205 voltage with only 7.5 ampere current peaks. It means high performance with the minimal hardware requirements. Third, the proposed method is suitable for the low-cost and embedded system, requiring only 16 rules and modest processing capability, ideal for automotive microcontrollers. Finally, it contributes to sustainable electric mobility, reducing hydrogen consumption improving powertrain lifetime and supporting linear transportation. Overall, this fossil approach represents a step forward in intelligent, sustainable energy management for electric vehicles. This is a this diapositive displays the some reference which is based on work, and we need to this so grateful and acknowledgement for the Universidad Politécnica de Guanajuato for funded this work, thanks to the support of automotive engineer career direction for the Universidad Politécnica de Guanajuato, and the idea by the Instituto Tecnológico de Celaya from the Laboratorio Nacional CONACYT de Electromovilidad, LABNACE. Thank you for your time. See you.